Great. Okay. Well, it's week 6. It's week 6 Tuesday. Our last day, our final exam will be in 2 days on Thursday. And I just want to check in with you guys, see how you guys are all doing. Are you guys excited, looking forward for this summer session to be all over? Yeah, more or less? Okay. And then you guys have, what, 2 weeks before school starts back up? Or some of you are all done? Who's going to, wait, no, I don't know. Is anybody here going to be all done after this class? All right, congratulations. Okay. All right, I don't know if you guys have any questions for me, but let me talk a little bit about the final exam. Let me make this big. Okay. So final exam. What do I have to say? All right. So it'll be Thursday. Did I already cover what's going to be on the final? No, right? Okay. I just want to make sure I'm not. Okay. So Thursday in class, 1 hour, 50 minutes. Handwritten. Okay, bring a calculator. What is that bad? And bring a ruler. Okay. Yes.
Is that your requirement, the calculator? You have to use scientific or
any calculator, just any calculator, but not your phone or computer or iPad, or something that connects to the internet. All right. So any calculator is fine, right? Just.
What's the ruler for?
I'll tell you, okay? But I'm just telling you, bring a calculator, bring a ruler, obviously bring a pen or pencil, an eraser. I would say pencil and eraser. All right. Pencil and eraser. Unless you're absolutely sure you'll make no mistakes. Okay. All right, let's see. Okay, so questions that you might see. All right, so I'll probably have just a few floating point arithmetic questions. Like similar to homework. Stuff like, what is the smallest normalized value, I don't know, whatever, etc., etc. Okay, stuff like that. And then we will have questions covering numeric methods. And this will be like manual iterations of a numeric method. So for example, I can give you a function. For example, I give you the function f of x is equal to, I don't know, x cubed minus 4x squared plus, I don't know, 4, no, plus 2. Okay, and then I say, let me just make sure, is this right? 1 minus 2. And I'll say use, I don't know, fixed point iteration to find a root of f of x. And then, well, maybe here, let's just say use, we'll start off with Newton's method to find a root of f of x, starting at x0 equal to 5 or something like that, okay? And then you then you perform 2 manual iterations of Newton's method, Newton-Raphson method, right? So you will find x1, then use x1 to find x2. Okay, so obviously, you can see why you want to calculate it, right? And then the ruler is so use the ruler to draw, the tangent lines and where the next iteration goes. Okay. Yes.
So for the function, do you have to start from scratch, or like you already provide like a graph of the function?
Yeah. So okay, yeah. I'm sorry. I will give you the function, and I will provide a graph of the function. All right. So that'll help. That'll be helpful. So I'll provide the function and the graph. You got to figure out for Newton-Raphson. You got to figure out the derivative. You got to figure out, I don't know, x1 and x2, right? So, all right. That's just an example, okay? So, but you should, be familiar with all of the numeric methods covered. Okay, which we have a fixed point iteration. We have Newton-Raphson method, secant method. So these are all root finding methods, right? And bisection method. So just consult textbook. So, and then we have optimization / minimization, optimization. So that's right. And so here we have all the same, right? Fixed point iteration on the derivative, Newton-Raphson method on derivative, secant method on the derivative, okay? And then golden section search. Okay, and then maybe we'll also throw in coordinate descent. Okay. Or we'll say a two-dimensional function. Okay. So, so in all of these, so I'll probably have maybe 2 or 3 questions for this section where I present a function and I tell you to either find a root or find a local min, local max using one of these methods. Okay, so you got to use the method I specify, right? So I'll say, here's a function, and use secant method to find a root or something with these starting points or here's a function, use Newton-Raphson method to find a local minimum or local maximum, okay? And you would need to know, you apply Newton-Raphson method to the derivative, right? All right, are there questions on this? Yes?
It's going to be manual as well.
It's going to be manual, yeah. And so you'll find x1, and I'll probably say like round to 3 decimal places or something like that. Because you're going to be doing 2 iterations. So the first iteration, I'll give you like a nice number that's not going to be like crazy or something, okay? And then you'll use the algorithm to find your next value, and then you'll take that value you find to get the second value, right? So you find your first value, and then you find the next value. And so I'll just say like round to 3 decimal places or something like that. So it's just so you don't have to type in this 10-digit number into your calculator. Okay. Right. Are there any questions on this? Okay. And then after that, let's see. All right, and then we'll have a randomization test and a bootstrap test. So in both cases, I will provide some, I don't know, a description of a scenario. I'll provide a description of the data collected, and then and I will ask a question about what the data says, okay? And then you will need to decide what hypotheses to test. So the null and alternative. And then you will write some manual code to perform either a randomization test or bootstrap test. Okay? And then, be ready for using package boot or writing randomization test, and we'll just do non-parametric bootstrap test, or writing manual code for a non-parametric bootstrap. Okay. All right, and then make sure you have a line to estimate a p-value. Make a conclusion. Okay. Is that okay? So I would say pay careful attention to the code examples I have provided, in the lecture notes. Okay. Yes, question.
Two questions. The first one is, so we can use either one of them, the package boot or manual.
I will tell you which one to use.
Oh.
Okay.
And the second question is, so like what part of code do we need to write? Like all of it, or just like, I don't know, like all of it?
Yeah. Wait, when you say write all of the code, I mean, like a randomization test is 6 lines of code, something like that, right? I don't know. I feel like it is. You have one code to kind of set up your data. Like, so for example, like, I don't know, here's an example, right? We'll say Mythbusters collected data. And it's like, so this is control, no, the other way around. Treatment and control, right? And I forget, yawn and no yawn, and what was, how many were the other one? 10, right? Yeah. Okay. All right, and then I say, do a randomization test. To test if the control group is more likely to yawn. Okay, so all right, so let's do our hypotheses. This will be question part A. What are the hypotheses? Okay, so the null hypothesis yeah, okay, so it'll be the proportion of treatment that will yawn is equal to proportion control. Right? Okay. And then the I'm sorry, not control group. I have this wrong. The control group is less likely to yawn. Right? Okay, do a randomization to test if the control group is less likely to yawn. Okay, so that's the null, and what's the alternative? So P treatment is greater than P control, right? Okay, so there you go. Those are your hypotheses. And then what's the next part? So you write the thing, then you write some code. Okay, so what's the code we have to write? Yeah, so we'll write pool is C, and then we're going to repeat whatever you want to repeat, right? So we'll repeat true 10 times, repeat false 24 times, repeat true 4 times, repeat false 12 times. Okay, so there's your that's your pool of data, and then we'll create a results vector. Repeat NA, I don't know, 5,000 times. And we write for I in 1 through 5,000. What do we do? So we'll do shuff. I'm going to just call this, and then we'll do sample pool, right? And then we'll call this group A. Maybe group A will be what? Shuffle 1 through 34. Group B shuffle 35 through 50. And then results I will be mean group A minus mean group B. Great, okay. All right, and then to get your p-value, I guess I should probably, I need to calculate observed difference first, right? Okay, observed difference is going to be, it's really just 10 over 34 minus 4 over 16, right? Okay, so here the p-value is going to be mean of results greater than observed difference. Okay, this is 100%. Full credit for this if you write this. Okay, greater than or equal to. I mean, it's not gonna. Yeah, I guess greater than or equal to. Sure. Yeah.
And I guess we normally add absolute value to the.
If it were a two-sided test.
But for the observed difference part, do we need absolute value for that part?
Well, in this case, the observed difference is greater
Yes.
than 0, so it's okay. It depends. Whether you put absolute values here or not will depend on the data and the situation and the alternative hypothesis. Okay. All right, so I'm sorry, maybe this was more than 6 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 lines of code. Okay.
Shall we set seed?
No, you don't have to. I mean, you don't have to set seed. You're writing this on paper, so so setting a seed's not gonna, right? Not gonna matter here. All right. Is this okay? All right, and so you'd write that, and then okay, there you go. Your data might be categorical like this. It could be numeric, okay? And just be prepared for either calculating a proportion or a mean, right? Description of the data collected. All right, and I'll just write. Could be categorical or numeric data. I don't know, maybe I'm giving away too many answers here. Okay, but is this all right? Okay, so I think that'll be it for the final, okay?
It's nothing from midterm then?
Nothing from before the midterm. Oh, here, one more thing. I guess maybe I might throw in like a few conceptual questions. Just like real basic conceptual questions.
Like what?
You guys are like scared. It's not for non-parametric Bootstrap, what assumption are we making about the population? No. Yeah, okay, you see, you would have gotten this wrong, right? So, okay, so, all right, let me just write this down. All right, so, I don't know, just a few conceptual questions, all right? So, I'm not going to tell you what they are, all right? Example, you know, what assumption are we making about the population and data when we perform non-parametric Bootstrap? Okay, what's the answer here? Anybody? Yeah.
So we will not be tested on our best that lecture because that one is before.
Well, let's get this first, all right, and then I'll answer your thing. Okay. Anybody want to take a stab at this? Yeah.
Isn't it you randomly sampled, so it's
Yeah. So we assume that our data is representative of the population. Okay, and that I guess duplicating our data can I don't know, take the place of the population. And I mean that's what we're doing when we do non-parametric bootstrap, right? Okay. All right. So and other another similar conceptual questions. All right. About, I don't know, computational statistics, right? All right, other similar, I don't know, questions. What's another one? Okay, which root finding method is, which is the only root finding method guaranteed to converge on a root?
Is it fixed point?
Bisection method, or I don't know. Okay, or I don't know. When will fixed point iteration converge? If the derivative at the fixed point is less, absolute value of the derivative at the fixed point is less than 1. Oh, you guys are scared now. Just a few questions, all right? Just a few conceptual questions. Okay. All right. So yeah. Okay. No, I won't put in no rvest. All right, here, this is the happy part. Okay, all right. So no rvest, no regular expressions, no. Oh, okay. We'll do no parametric bootstrap. Yeah, I don't know. Is there anything else I covered that I didn't mention? Yes.
stringer and dplyr.
Yeah, no stringer, which is regular expressions, or dplyr, or tidyr, or lubridate. I don't know. Okay. All right. Anything else?
Could you please clarify the last homework problem, like the
Is something going on with homework 5?
light one?
Okay, speed of light. What about speed of light?
So you have to shift the data.
Because the average is 26.
Yeah, it's not 33.
Right.
Right.
So you want to know is your average of 26 significantly different from 33, right? The homework's due on tomorrow, though. I'm afraid of that. Well, whatever. All right, I'll give you your answers. Okay. Well, not complete answers. Okay. So this is, what is this? Homework 5? Number 5? Okay. Speed of light. You should read how people measured the speed of light, right? It's pretty impressive. They had like a mirror that rotated, and based on how fast the mirror, because it was like whatever. All right. Because all right, so I'll draw a little picture, right? So you bounce the light, and then it goes, and it hits the mirror and then it comes back, right? But and this mirror is rotating so that by the time it bounced back, it this is the worst picture I've drawn. Okay. All right, forget this. All right, okay. Here's the thing: is your sample of data significantly different from 33, right? And so we're doing Bootstrap, right? Okay, so basically your null hypothesis will be what? Mu is equal to 33. Mu is different from 33, right? Okay, and then we use Bootstrap to basically create a sampling distribution of X bar. And we want to know basically the probability of getting a sample different from 33. Well, okay. All right, so I don't know the exact thing, but let's pretend our X bar is equal to 27, okay? So we have a difference of 6 points between 33 and 27, right? So let's pretend X bar is equal to 27. Okay, so our observed difference is equal to 33 minus 27, which is 6 points. So it's technically it should be 27 minus 33 equals -6. Okay, so we have an observed difference of -6. We're using a not equal sign, 33. Okay, so your Bootstrap code would look something like this, right? So what's our data? Light. Okay, so light is our vector of numbers, right? 27 dot. Okay. All right, we'll do results. See, this is manual, so I'll repeat NA. I don't know. We'll do 10,000 times, and we'll say for I in 1 through 10,000. What am I going to do? I'm going to call something called resample. And what do? I sample light replace equals true, right? This is very important. And then what do? Results I, mean of resample. Okay, and then, oh, and then here we have observed difference is equal to, yeah, we'll do mean of light minus 33, okay? All right, and so technically my observed difference is around, is -6, okay? So our p-value is two-sided, right? So we have a two-sided test. Okay, so this means we want to see how often is our resampled mean greater than 33 and or less than 27 minus 6, 21, less than 21. Okay, because our observed difference is 6 away, so we want to know how often do we end up 6 away above and 6 away below in the opposite direction. Okay, so how often is our resampled mean more than 6 above and more than 6 below? Okay, so how often is our resampled mean more than 6 above or more than 6 below? Okay, so basically, just to kind of simplify it, I will do upper is going to be equal to 33, and then the lower bound will be equal to the mean of light minus the absolute value of observed difference. Okay, and then we will ask the mean of results greater than 33 or results less than the lower bound. Okay. And I think this is like close to 0. If you do it 10,000 times, it's like. Yes, question.
Can we shift the data so its mean is 33 and then do 33 plus observed difference?
Okay, so you just shift your data away from, so you subtract 33 from everything?
You subtract the mean and add 33 from everything.
You subtract the mean and then you add 33. Okay, and then.
So the mean is now 33. Then you do the bootstrap as we did.
Okay, and then, okay, so then on the lower bound you want to know how often, so we've recentered the mean of our data to be 33, but then we compare it to the original mean of the data, less than that, but then you also have to go in the opposite direction of being 39, right? So you want to say how often is our resampled things less than 27, and how often is our resampled thing greater than 39? That's fine.
Okay.
To me, it feels like a few extra steps, but it's fine. I mean, mathematically, it's mathematically, you're effectively, if you subtract the mean and you add 33, mathematically what you're doing is you're adding on observed difference to all the values. Okay, so if you add observed difference to it, then it's then your lower bound is mean of light and your upper bound is 33 plus observed difference. So that's fine. Question?
Yeah, so we do get results of 0, and then you say you want us to like talk about it.
Yeah. So you would say something like, Bootstrap resamples of our data did not produce any sample means that were greater than 33. Therefore, we have evidence that our sample mean is significantly different from 33. Okay. If this happened, if the mean of all of these kind of results logical checks was greater than 5%, then you would probably say, ballpark 5%, right? Greater than that, you'd say our sample mean is not significantly different from 33. Okay. Should I write that on the screen? Here, I'll go ahead and write it. All right, so you can say something like we created 10,000 or we performed 10,000 Bootstrap resamplings of the data. Okay, none of our resamples none of the resampled data had sample means that were greater than 33 or less than lower bound. Okay, this provides evidence that our sample mean of 27 or whatever is significant different from 33. Okay. All right, so we'll say in an alternate universe, if many of the resamples were greater than 33, so say over 5% of these samples, okay, you can write, okay, so we would write this and you'd say, I don't know, 8% of the resampled data had sample means that were greater than 33 or less than, so this means that our sample mean of 27 is not significantly different from 33, or I don't know, something like that. Yes?
Could you please clarify the p-value of the light speed example?
So the p-value is the probability of getting your data or something more extreme if the null hypothesis were true.
Yes. So
Yeah.
for the lower part, the value go lower, why are you subtracting the absolute value?
So I'm saying in our sample data we got a mean of 27. Okay? Now I'm saying 27, how different is that from 33? It's 6 units away. Okay? And you know, we could have gone 6 units away, you know, on the lower side, or 6 units away on the upper side. And so we want to know how often are we going to get a difference, I guess, greater than 6 away from what we observed. So when we resampled our data, we want to know, okay, 6 above our mean of 27 is 33, so we want to know how often are we above 33, and 6 away from our mean on the other side would be 21. How often are we below 21?
So when we're doing like 2 sample tests,
Uh-huh.
In your lecture notes,
Yes.
you never do the shifts. So
Well, if we have 2 samples, it's handled by doing the absolute value against the absolute values.
yes.
Yeah.
But if we only have 1 sample, we just like go over like this.
Yeah, we could, okay, rather than doing, so over here, we recorded results as mean of resample, okay? We could have recorded results as resample minus 33.
Mean of resample minus?
Yeah, mean of resample minus 33 or mean of resample minus 33. It doesn't matter because the mean of 33 is 33. So So we could have thrown in a minus 33 here, and then we would have done results greater than observed difference or results less than negative observed difference, which would be the equivalent of doing absolute value of the results greater than absolute value of the observed difference.
Please write it down.
Yeah, sure. Okay, so we could I could, you know, inside here we have for I in 1 through 5,000, this is another possibility. I could have done resample to be sample light replace equals true. Okay, and then I could do results bracket I is going to be equal to the mean of resamp minus 33. Okay, this is one possibility here. Right? Okay, and then for the p-value, okay, so we have observed difference will be mean of light minus 33. Okay, and the p-value could be the mean of absolute value of results greater than absolute value of observed difference. Okay?
This is different from the...
No, this will be equivalent, right? This is equivalent to...
No, not equivalent.
But didn't do a shift.
Yeah. The lower bound is different.
Just like in a loop, you should minus mean light, not 33.
Yeah. In the for loop,
In a for loop, you should
minus mean of the
mean
light.
light.
Oh, mean of light. Oh, okay. Sorry. Absolute value of the results greater than absolute value of observed difference. And this should be equivalent to mean of results greater than observed difference and negative observed difference or results less than observed difference. Okay. Yes. All we're doing in all of these things is we're just like adding or subtracting a constant somewhere and shifting things around. I'm pretty sure these will all give you the same results here. But we can, I don't know, maybe I've made a mistake somewhere. But you know, where you add or subtract as long as you're consistent in the constant you're adding or subtracting, it's fine. Question?
Yeah, is it okay if I calculated the 99% interval
Yeah.
of the Bootstrap sample?
Okay.
And then see if 33 lies between that interval.
That's fine.
If it lies in the interval, then it is a second difference between these.
Yeah. I mean, you can look at all of the values of your 10,000 and create a 100% interval based on your 10,000 things, and you'll also find 33 is not in there. But yeah. Yes.
In the last code that you wrote, you rewrote it to mean of resample minus mean of light instead of 33. Why is that? Mean of light is like 20, 27, 26.
Let me think. I think my original feeling is I should subtract off 33, but then...
But if you subtract 33, you will get a different answer from the first one.
Okay. guys are all throwing stuff at my brain here. We're resampling our data, and the question is our sample different from what we observed? So you know, my brain is used to thinking of it this way. We find the mean of the results, and then we subtract, you know, we create an upper and lower bound. If we resample our data,
So can you explain again why in this way we are using the 21? So why is 37 minus 6 not 37 minus?
because you want to know, can you get something, you know, what you observed is that your data is 6 units away from what it should have been. Okay, and so you just want to know how often, just from random resampling, can you have a sample mean that's more than 6 units away from where you should be. Okay, and
where should be 33.
Where you should be 33. That's correct. But of course, when you resample the data that you have, all of your samples will be centered at your sample mean. Okay? So, you know, because you're resampling your sample. And so, of course, all of those resamples will be centered around your current sample mean of 27. So, I think, let me just go back through my confused brain here for a second. And I think I'm supposed to subtract off 33, but let me just double check. Okay, so if I'm resampling my sample, I'm going to take the mean of my resampled data. I'm going to subtract off okay. So here, we do the mean of light. Yeah, that's fine. Okay, and this means we expect results to be centered around 0. Okay, that's correct. Okay, so we expect our results to be centered around 0, and here we want to know how often do our resampled bits end up more than 6 units away, or more than 6 units away on the positive side, or more than 6 units away on the lower side. So this is correct. Mean of resample minus mean of light. Okay, because by subtracting off the mean of your data, this is being your sample mean, you are expecting your results to be centered around 0. I'm making this worse, okay? Because when we do this step, right, we are sampling light with replace equals true. We've taken our current sample. Light is our current sample that we've duplicated a billion times. Yes. And so light, this thing, light, has a mean of 27, right? That's what we're saying, okay? I've redrawn a sample, and when I redraw a sample from here, I'm expecting to get a sample around 27. Because of random sampling, maybe it's a little bigger than 27, maybe it's a little bit smaller than 27, okay? And so when I take the mean of my resampled data and subtract the mean of light, I'm expecting to get something around 0. Sometimes a little higher, sometimes a little lower. I want to know how often, when I do that, will I end up getting a sample whose mean is more than 6 away, or more than 6 away above, or 6 away below. So yes, we do subtract off mean of light. Okay, sorry, I just had to stop and think for a second. Is this okay?
Is this gonna be on the final?
Not this exact problem, but
Is it going to be one sample, like Bootstrap?
So my recommendation is to look at the problems I gave in the homework and in the lecture as examples for conducting a Bootstrap test. Okay.
So you include one sample question.
Right. One or two samples. I mean, you have to stop and think what the important thing is. Stop and think what your hypotheses are, and then how you should conduct your Bootstrap test should kind of naturally flow from that. You know, how are you going to resample your data? I'm getting angry looks. I don't know. I'm happy to try to answer any of your other questions as well. Other questions from the homework?
And also for this one, can you use boot?
You want me to do how I would do this with boot? Okay. If I want to, yeah. Okay. All right. So using package boot. Okay. So we still have light, which is 27 whatever it is. Okay. We have to create a function. So we'll call this light func. And our function is always a function of data, comma, index, right? So first thing we do is we're going to subset our data based on the index. So with it being one sample, I can just use single brackets, all right? So here, taking the D and subsetting data based on index is basically doing this step here, okay? And therefore, once we do that, then what we will return is just going to be the mean of D. There's your function. And now the Bootstrap will be boot light function and let's do this 10,000 times. Okay, and then we'll put these in results. Okay, and then what we will have is our p-value will be results $t, and what we want is the mean of, I've got to put this in absolute values, greater than absolute value of observed difference. I guess I need a line for observed difference, but that's earlier in the code as well.
So can we do this in the homework, or we have to run the code for the homework?
Yeah,
Can I use boot in the homework for question 5?
What's that?
Can I use this one? Like the
Yeah,
boot-
either way, you get the same results, or about the same results. Yeah.
So for a light function, how come you don't have to pass any arguments?
Oh, actually, I'm sorry, I did this wrong over here. How come I don't have to pass any arguments?
Yeah, for light underscore function, like the data set and then the index.
Yeah, I did.
No, when calling it in the boot function.
Oh, you don't specify any of that. The boot function passes the arguments for you. This should be absolute value of, not this. It's got to be results greater than 33 or results less than mean light minus observed difference. That's what we have here. So it's a little bit tough. I'll admit. Randomization tests in Bootstrap, we're revisiting all of the hypothesis testing that you've covered in your intro stats class, but without any assumptions about the central limit theorem. And so we have to generate the source of randomness ourselves. Okay. But the nice thing about this is central limit theorem only applied to means, and Bootstrap and randomization tests can then be expanded to other things like standard deviations, standard errors, correlations, things where you might not have a full grasp on the sampling distribution. Okay. Like correlations follow a t-distribution with n minus 2 degrees of freedom and stuff like that, right? So. More questions?
Yeah. Why is the 33 when the result is larger than 33? Why is it not like result is larger than mean of light plus observed difference? Is it because
Wait, mean of light plus observed difference is 33.
But it should be like that.
I can do that. But yeah, mean of light plus observed difference is 33. So that's
Yeah, that's just a coincidence. But
no, it's not a coincidence. That's by definition. Observed difference is the difference between mean of light and 33. So mean of light plus the observed difference is going to be 33. We've defined observed difference as the difference between 33 and the mean of light. So if we add that back in, we're of course going to get 33. Not a coincidence, yeah. Yes? Can I what? Oh, I need a $T, you're right. All of these things. Little details here. Okay. Well, this was intended to be an encouraging lecture to say, oh, you know, the final is totally doable. And I still believe it. I believe the final is totally doable, and it's not, I'm not intent out to like try to get you or anything, okay? Study your homework 5 and the examples covered in lecture for these sections, okay? And then make sure you can do the manual iterations. Bring your calculator, bring a ruler here. Okay. All right, any other questions about final exam content we've covered in the class? Okay. I have some stuff that I could talk about that I think are interesting. I'm not going to test you on this. Don't just get up and leave, but so one thing I like to cover is kernel density estimation. Have you guys heard of this term, kernel density estimation? No? Oh, okay. This is basically, you can think of this as like smoothed out histograms. So, for example, rude. I can create, like we might say we have some data. Our norm, let's draw 100 values from random normal, and then I can just create a histogram of X, and it looks like this, right? Here's a histogram of X. I can also create a kernel density plot. And this is just done by doing plot density x. Okay, and this creates a kernel density estimate. All right. Let me just say, let's do 10,000. Here's your histogram x, and then here's your kernel density estimate there. Other things, so for example, we can generate data from the exponential distribution. Let's say I want 1,000 values from the exponential, and we'll say rate equals 1. Okay? So a histogram of x will look like this. This exponential distribution is like, how long will your light bulb last, right? And you say, I plugged in my light bulb. Well, I don't know. Do LED light bulbs also follow exponential? It used to be like, what the incandescent bulbs, which used a ton of energy, followed an exponential distribution and stuff, and this is what we expect, right? And then, and if we did plot density, we get something that looks like this, okay? One thing you'll note, though, is if we look at the density graph, we're getting values, we're getting stuff down here, below 0, right? Which doesn't make sense for the exponential distribution, okay? Because the exponential distribution can only produce positive values because it's like, how long will something last? It can't last a negative amount of time. But something happened. But what's going on is that the kernel density estimate thing is basically just taking our histogram and kind of smoothing it out, okay? So the histogram correctly shows no negative values, okay? But the kernel density thing shows some negative values, okay? But it's not, there's actually no values down here that exist, okay? And you'll see things, I think later on, you'll get plots, density plots, okay? And these density plots, these kernel density estimates, are ways to kind of get an idea of what the distribution looks like without kind of getting, without getting bogged down with maybe some of the bumps that might appear in a histogram, okay? So for example, if I did histogram breaks equals 30 or something like that, okay, this is what 1,000 random values drawn from the standard normal distribution look like, okay? This is a histogram, and you can see it's a little bit bumpy. The density plot tries to smooth this over. Okay, you have a bandwidth parameter. You can make a smaller bandwidth, which will make it, I guess that's not the correct thing. Oh, I have it in the wrong thing. I want density of x with a bandwidth of 0.1, okay. And a lower bandwidth will make it a little bit more jagged, and a larger bandwidth will make it a lot smoother, okay. And you can kind of see how changing the bandwidth allows for a little bit more, I don't know, jagged notion of what's going on inside the histogram, okay? So anyway, the kernel density estimate is a way for us to kind of draw these smoothed out histograms. So, instead of getting something that looks like this, you get something that looks like that, okay? And we've only been able to draw these things with the help of computers, okay? And that's why I throw this under kind of computational statistics. Because here, this is just an estimate of what perhaps the underlying, what the PDF looks like, right? Your PDF is the function that defines the density of the probability distribution. And this curve, it looks nice, but there's no actual functional form for this, okay? It's just an estimate, okay? Just like these are all things, and I mean, can you imagine the mathematical formula for the function that looks like this? It would be a tragic mess, okay? We don't actually, kernel density estimation is a purely, or it should be, like a purely visual tool, okay? It's not that we can plug this in, get this thing, and then now we have a functional form of the density, okay? That's not its intended purpose. Its intended purpose is to give us, you know, nice looking graphs like this, so that we have an idea of what the density looks like. Much like a histogram is supposed to give you an idea of what the distribution looks like, and this is also supposed to do the same, just supposed to give us an idea of what the distribution looks like. So it's kind of like smoothed out histograms, okay? Should give us a nice smooth curve. That resembles the density curve, okay? Okay. It will not give us a functional form of the density. Okay, so you can't then use this to say, oh, okay, this is the probability density function. Okay, the way it works, though. Okay, so let's just kind of review how a histogram works. How do you draw a histogram? Like if I give you some data and I say, take these 40 data points and make a histogram, what would you do? What's your first step?
The histogram function.
Not use the like if you had to do it by hand, what do you do? Yeah.
Decide how big.
Yeah, you create these bins and then you tally up how many points fall in the bin, right? And then you basically, so histogram, so the manual method, set up some bins, okay? Tally up the bins, or tally up data points that fall in the bins. Okay, and then you draw, right? And you can think of each data point, like if you had something like this, each data point is basically gets a brick in the histogram. And so here, you know, if the bins were drawn like this, right? And this would be kind of your histogram. You can think of you're dropping a brick for each data point that you have, and they stack up, okay, based on where they fall in the bins. Okay, kernel density estimation. Draw, and then we can think of this as drop a brick in the bin for each data point. Okay. With kernel density estimation, we're doing something similar, except we're not going to drop a brick. We're going to drop, you have to think of like a soft wire mesh, or a soft, I don't know, Jello mound centered at each data point, okay? So imagine instead of dropping bricks, dropping a soft wire mesh or, I don't know, jelly mound, okay? Centered at each data point. So in the just for illustration, we will start with rectangular kernels. Okay, so if I have, here's one data point and here's another data point, I will drop a rectangular jelly mound here, and I drop another rectangular jelly mound. And this is what my kernel density estimate will look like. Okay, so we'll just say this is 0, and this is 1, and this is what it will look like. Okay, and here, let me just kind of illustrate that. And so I'll say x is the points 0 and 1. Okay, and then we're going to do plot density of x, and kernel will be rectangular, I think, and then we'll do bandwidth equals 0.1. And there you go. You have it. The scaling looks a little funny, but you've got basically a rectangle dropped here and a rectangle dropped here. It only looks super tall, but it probably, well, that's not any better, but there you go. Okay. I could drop wider rectangles. Okay, so I'll still say centered at 0 and 1, and we've got, you know, a data point at 0 and a data point at 1. And let's say I drop a wider rectangle like this. This gets dropped down, and then I've got another rectangle over here, and this gets dropped down. What will happen when these rectangles fall? Okay, the overlapping part will stack, and what we will end up getting is something that looks like that. Okay, because you have to think of, you're dropping these rectangular jelly mounds. One falls down at 0, and then another rectangular jelly mound centered at 1 falls down, and the part that overlaps just kind of blobs up on top of each other. Okay, and that's what will happen if I create a kernel density plot, this time using wider rectangles of, let's say, of 0.5. Okay, so, and you can, well, here, let me just, maybe this is a little exaggerated here. Okay, so here I'm centered at 0. Here's a data point centered at 0, and it drops a rectangle, and then a data point centered at 1, it drops a rectangle, and then the overlapping part forms this funny shape here. Okay. What would happen if if I take 0 and 1, this, you know, these are getting dropped, and then let's say we have one at 0.5. So we have 3 mounds of rectangular jelly falling. Okay, what would the resulting shape be? Yeah, it would look kind of like this, right? for, I think, 0, 0.5, and 1, okay? And so let me just do that. 0, 0.5, and 1. Okay, so here we go. So if I do a small bandwidth, I have 3 rectangles separated. If I make the rectangles wider, they stack up and they form this, okay? And you can kind of see rug x. This shows where the actual dots are. Okay, so these are rectangular kernels, and rectangular kernels are fine, but you get like these kind of crazy jagged things if you do if you say if you want a rectangular one. Okay, this is what a rectangular kernel ends up looking like for 100 data points. Okay, and you can kind of see on the edges we have kind of a little bit of these rectangular things, but it looks like super jagged, and generally we want something a little bit smoother. Okay, and so the default behavior of kernel density estimation will be don't drop rectangular mounds of jelly, but drop normal shaped mounds. Okay, so the default kernel is the Gaussian. And basically, we drop a normal curve at each point. So, if you have if you have got data points at 0 and 1, you know, imagine dropping a curve here and dropping a curve there. What will the resulting curve look like? It'll look like that. Okay, if you're dropping these kind of these hill-shaped mounds, okay, or if you choose to drop a wider kernel, if we have 0 and 1, and you're going to drop something really wide, okay, then you might get something that looks like this, centered over 0 and 1. Okay, and I'll just kind of illustrate that here as well. So I'll just say here I'm dropping 2 separate Gaussian curves, one centered at 0, one centered at 1. If I, let's just make the bandwidth a little bit wider, we'll get that. And if I make the bandwidth even wider, we'll get something like that. And if you make it really wide, keep in mind the data points are centered at 0 and 1. Okay, so we've got skinny hills being dropped at 0 and 1, slightly wider hills, and so the center part gets overlap, and then as they get wider, you get stuff like this. Okay. Okay. So anyway, that's basically what happens. We don't draw density curves at when you only have 2 data points in your data set, but when you have a lot more. Okay, and obviously trying to draw this yourself would be like an impossible task, but the computer is able to quickly add up all of the points and see how all of these curves stack up very quickly. Okay, so it can do, you know, when you say here are a bunch of random values, and make a plot, a density plot using Gaussian kernel. Okay. These are the dots that represent the 100 random values drawn from the standard normal. Okay, all of these little lines here. And so the computer is able to say, okay, I'm going to draw a little hill centered right here. I'm going to draw another hill centered here. And when those two hills overlap, we're going to get something that looks like this. Okay, and over here I draw, you know, some kind of hill type of thing, right? You can you know, you can see all the stuff that we get here, and you can just kind of see what happens if I mess with the bandwidth equal to as, you know, this gets a lot more jagged and stuff. And so you can see when the dots kind of overlap, they form this, and it gets messy, but the computer is able to just add up all of the hills very rapidly and create this plot together for us. But again, you don't get a functional form, you just get the resulting curve of adding up a whole bunch of little mini Gaussian hills centered at each data point. Okay? And you're just kind of stacking these mounds on top of each other. If you check the help for density, you get a variety of kernels that can be used. Okay, I would say Gaussian is probably the most common, but you have Epanichnikov, which is really just an upside down parabola. Okay, so let me just kind of show all of these here. So if we have 0 and 1, you can have Epanichnikov, which is upside down parabolas. You can have a triangular, which is just triangles. It's exactly what you would expect. So the triangular ones, I think you can start to see, like if I dropped wider triangles, what would happen? You get something that looks like that. Okay, it's like cat ears or something, and even wider, you get this business going on, right? So anyway. With the Epanichnikov, so this is 2 upside down parabolas. As we increase the width, you get this funny shaped business. Okay, and stuff like that. And again, the computer can handle all of these things very quickly. So this is a rectangular, this is triangular, this would be Epanichnikov. Okay, and then the default being Gaussian produces kind of your, in general, smoothest settings. Okay. All right. Well, anyway, that's kernel density estimation. I'm pretty sure you will encounter this in the future. And is it important that you know how it works? Probably not, and I'm not going to test you on it. But I think it's kind of nice to know, like, oh, when you see a density curve like this, where did this come from? It's coming from the computer just taking these mounds and stacking them on top of each other and seeing where the resulting stack ends up. Okay, because this is a common plot used to display the shape of your data. Okay, any other questions? Any, I don't know, topics you want me to try to tackle in a couple minutes here? In general about, yes?
Can you give like an example of how we'd see coordinate descent on the final?
How we might see coordinate descent on the final? Yeah, it'd probably be similar to the homework, except I won't have you do golden search. Okay, we'll do like a coordinate descent example, right? So I'll provide some. So this will be coordinate descent. Okay, so you got some function f of x and y, okay, equal, I don't know, blah, 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 right? Okay, and then I'll probably give you some starting point. So I'll give some starting point, and I'll say x0, y0 will equal, coordinates 5, 5, or something like that. Okay, and I'll say hold x constant and perform coordinate descent. All right, what's the first thing you do? So I don't know let's. I don't even know if this. We'll say x squared minus 4x minus 5xy minus 3y plus y squared. Okay, I don't know. Is this even a thing? Who knows? All right, let's just say this is your function here. So we'll say hold x constant and perform coordinate descent. Okay, so then what do you do? So now you will do x0 equals 5. Okay, and then so you'll say f of x, y, where x is equal to 5, becomes 25 minus 20 minus 25y minus 3y plus y squared, right? And this looks like 2 to the 5th. It's 25. Okay, so then what is this? 5 minus 28y plus y squared, is that right? Did I mess that up? No, that's correct. Okay, and then what do you do? So you have to find the minimum with respect to y. Okay, so what's the minimum? Or actually, it's not find the minimum. Find argmin, right? Find argmin y. Okay. Okay, and then so you're like, all right, so I've got f of y is equal to y squared minus 28y plus 5. And then you'd say, okay, d dy. So like, how do you minimize this? You will just do take the derivative and set to equal 0, right? Take derivative, set equal to 0. Yeah, and also if you know the form of a parabola, you also know that if you've got a minus something, like whatever it is, it's going to be half of this, right, on the positive side. But anyway, we'll just go y squared minus 28y plus 5. This gives you 2y minus 28, and you solve, and you get y equals 14. Yes?
Are we allowed to use differentiation on the final, or are we going to be required to find a minimum using some form of
No, of course you can use differentiation, because otherwise every minimization step is going to be like 20 iterations or something, right? This is not... For a computer, that's what you got to do, because the computer probably can't figure out, doesn't know how to differentiate, right? But you do, right? At least for polynomials, this is easy, right? So you say, okay, y equals 14. Okay, so now y equals 14, and then f of xy f of xy with y equal to 14 becomes, what do we have? X squared minus 4x minus 5x times 14, I don't know what that is, 70, minus 70x, minus 3y, minus 3 times 14, plus 14 squared. Oh man, okay, so anyway, you get x squared minus 74x. What's this? 168 minus 1114 minus plus 154? I don't know, something, right? Okay. And then you solve here. And then you get x is, all right, so minimize, and you get x equals 37 or something like that. Then you go on. Is that right? I feel like I messed something up. But anyway, there you go. Okay. I don't know if x squared minus, I'm curious now. But that's what a coordinate descent example would look like. I feel like I said too much here, but all right, let's go to Wolframalpha and just see what this thing looks like. X squared minus 4x minus 5xy minus 3y plus y squared. Oh. Okay, well this is no good because it's a paraboloid, so we'd get in trouble. Okay, but I'll find a function that's not a paraboloid, but not a hyperbolic paraboloid, but just kind of a something that's more bowl shaped. Okay. Okay, all right. I'll have to figure something out. But yeah, okay. But anyway, it would be something like that. You take the thing and you follow the path down. Is that all right?
So the tolerance in this case would be the next x minus.
There's no tolerance here. Oh, I mean, there's no tolerance when you're doing it by hand. I'm only going to ask you to do like a few iterations, okay? So I just want to make sure you understand the concept of plugging in a value and understand how to get the next value, and then how you plug that value in to get the next value, right? So here you plug in your x equals 0, and you know, did I miss something here? Okay, I don't know what happened, but okay, but anyway, that's what coordinate descent might look like. Are there any other questions? Okay. Well, I hope you've enjoyed the course. I hope you guys left reviews for me on the student evaluations, and if you're so inclined, please consider leaving a review on Bruinwalk or Rate My Professors or something. I hope you like the class. I'll have office hours, so if you have any questions, I'm happy to try to answer those. So, thank you.